thank you all for joining us today for our first webinar of 2021, which will be given by Wouter Buytaert on the role of citizen science in hydrology. I'm really pleased to welcome Wouter. He's a professor in hydrology at Imperial College London. He works on the interface between hydrological processes, water resources management and sustainable development, and has worked for over 2 decades in the Andes, where he founded a regional initiative for participatory monitoring of Andean ecosystems. Sounds super interesting, and perhaps, I don't quite know, we might hear a little bit about that today. No further ado, we still have lots of people joining, but great to see so many of you here. I'll hand over to Wouter.
Hey, thank you very much. Thanks indeed for the kind introduction and the invitation to give a talk about citizen science in hydrology. And I think it's fair to say that citizen science is very trendy at the moment. It definitely is on the minds of a lot of academics and researchers, witnessing the coverage in some high-profile journals like Nature Sustainability. And obviously the reason for that is very trendy at the moment within the scientific community, but also with the funders. Horizon 2020, for instance, has various funding streams to promote citizen science and citizens' engagement in general. Perhaps as a bit of a vaccine against fake news. But also within the UK, UKRI, NERC, for instance, has launched some recent calls to promote citizen science within the academic community. And also, if you look at large research and other institutes in the operational sphere, such as Kew Gardens, the Met Office here in the UK, many of them are setting up streams of activities around citizen science and increasing the engagement of citizens within data collection and knowledge creation. And lastly, you might have seen that the United Nations is launching has launched a draft recommendation for open science, which is on track to be adopted by the member states this year in 2021, which also has citizen science as an explicit part of the strategy to open up science and promote open science for sustainable and human development. So a lot going on about citizen science, and indeed a good opportunity to think a bit about how citizen science can be leveraged and used within hydrological sciences and the broader realm of water management and water security, and see what really are the opportunities and how can we make the best out of that. And let me start with giving a definition of citizen science. There's no specific uniquely accepted definition, but in general, it refers to the participation of the general public, non-scientists, in the generation of scientific knowledge. And I guess that most, if not all of you, already are familiar or know about some citizen science activities. There's some highly visible and long-standing citizen science projects. Think about, for instance, the NGO Earthwatch, which has set up and running for many years an international network of citizens that collects information about water quality. More within the academic sphere, there is the group of Jan Seibert and Ilja van Meerveld at the University of Zurich, who have been running for many years the Groundwater project, which is strongly built around the idea of a mobile phone app that allows citizens to take measurements about hydrological processes such as stream flow, soil moisture, and other variables. But indeed, those are just two of a large range of global citizen science projects, many of which have emerged over the last decades, a few of which we've reviewed in a recent review paper in Frontiers of Earth Science. So just as an introduction to show that there's a lot to do about citizen science, and that it's perhaps worth reflecting a bit about how we can promote it further, or what are the opportunities within hydrology. So that's what I'll do over the next half an hour, give you some reflections. And I should note that I don't consider myself an academic expert of citizen science, but more an expert from experience. And much of that experience comes from my involvement in the network that Lucy already mentioned in the introduction, a participatory network for the hydrological monitoring of ecosystems in the Andes. And so I'll start my presentation with telling a bit about that story of that network and how it evolved and how it shaped our thinking about participatory science and citizen science in particular. And then I'll go on with some more theoretical reflections of what those experiences mean and how we can structure those in terms of thinking about how to use citizen science, and particularly in the context of knowledge co-creation, because that's a bit another buzzword, or if you will, the holy grail of applied science. How can we implement knowledge creation together with end users, together with all the stakeholders involved of applying scientific knowledge to manage the hydrological cycle for the benefit of humankind. And I'll finish at the end with an example of a case study of how an IMEA site has helped to provide the evidence to implement nature-based solutions for water security of the city of Lima in Peru. So let me take you, at least virtually, to South America, and more particularly the tropical Andes, this mountain range that stretches along the Pacific coast of the South American continent, and which in itself is a very interesting system from a hydrological perspective, because it's really a melting pot of different synoptic climate circulations, the Pacific anticyclone, the Atlantic low-level jets, and they come together, interact with the topography of the mountains, and create a hydrological system of tremendous complexity, giving rise to different ecosystems and biomes, as you can see, and related hydrological processes that really range from the driest place on Earth, the Atacama Desert in northern Chile, to some of the wettest regions of the world along the Pacific coast of the Colombian Andes, and basically anything in between, leading to tremendous gradients and diversity in terms of hydrological processes, which in themselves are interesting for a hydrologist, but also are very, very relevant, very important for local human development. And indeed, mountains are often pitched as natural water towers, and in the case of the Andes, that's very true in the sense that they provide water to millions of people living in and near the mountains. And obviously, we know about glaciers and their contribution to water, but also many other ecosystems and landscape elements like mountain wetlands are very important in providing local storage capacity, buffering and modulating flows of rivers that descend from the mountains and that are diverted and used for water supply. So very important systems, which at the same time are under severe threat. And probably the most iconic victims of climate change are glaciers, which exist in the Andes, especially in Peru and Bolivia. But there's a lot of other types of threats, particularly agriculture. Increasing population growth makes people move up, and perhaps even climate change contributes to making those areas more inhabitable, and means that you get a higher density of population, which leads to encroaching agriculture and affecting those hydrological systems. And also forestry, deforestation is one of those big and well-known types of negative land use change. But also in these cases, there's a concern about forestry activities, and particularly the introduction of exotic species like pine and eucalyptus, which consume a lot of water, evaporated, and it inevitably results in less water running off and potentially affecting the reliability and availability of downstream water supply. So those are some of the specific pressures and concerns of local land managers about how to manage those ecosystems in a way that safeguards the hydrology-related ecosystem services. And obviously, the big challenge to produce a scientific evidence base to do so is the lack of data. So to tackle some of those issues, a bit more than a decade ago, when I was doing some research there, we teamed up with some local actors, very much driven by a local development NGO called Condesan, which has headquarters in Ecuador and Peru, and try and assemble a bit a group of interested people with the same concern of improving the evidence base and collecting data on the hydrological functioning of those ecosystems, because especially those at the highest regions, which are really the water towers, are also those that are least monitored by the traditionally available monitoring networks. So we started that and basically teamed up, joined forces to start monitoring, particularly of basic hydrological fluxes of stream flow and rainfall, to be able to compare them and really infer the impact of different types of land use change on stream flow and water availability. And so that network, we call it Hydrological Monitoring of Andean Ecosystems, and has really been going on now for slightly more than a decade. And from a hydrological perspective, the design, if you will, is that of pairwise catchment comparisons, which essentially is sometimes pitched as trading space for time. The main interest being in trying to assess the impact of catchment interventions, especially land management, on the hydrological response, where the ideal way of doing that is by monitoring a catchment before and after a change. But obviously that takes a very long time, is often not feasible. So the next best thing is to compare catchments that are hydrologically as similar as possible, but differing in one main aspect, which is land use, and then compare the hydrological response and try and attribute that to the type of land management. You can do that by, for instance, plotting flow duration curves, as you can see here on the right-hand side, and look at, try and infer trends in terms of the impact of, for instance, cultivation, which tends in those regions to reduce base flows because of artificial drainage, and the impact of afforestation with exotic species, for instance, shows very clearly how the total water, the runoff ratio drops because of the increased evaporation as a result of planting those species. That's a bit the setup, and actually has been very successful in the sense that we started off with a few catchments in Ecuador, but by now are monitoring more than 25 locations over Bolivia, Peru, Ecuador, and these days also Venezuela and Colombia, generating a wealth of information about the behavior of those ecosystems and the impact of different management types. Hydrology itself is a very useful data set, which is available, has been published in scientific data, so it's publicly available for anyone who wants to do further research. But obviously, this endeavor has not been without its issues and challenges. And those challenges range from very, very specific practical challenges. The cost of equipment, it's very much a grassroots initiative without any baseline funding. So obviously, the cheaper we can get the kits, the better. And there's still a constant struggle of buying and replacing damaged equipment and finding the funding for that. But also technically aspects like quality control, processing, training local people, developing protocols, translating them into Spanish is an aspect that takes a lot of time and needs us to think about how the more traditional or official protocols from, for instance, the World Meteorological Organization can be adapted to be applicable within that this kind of context. But also at a more fundamental level, it's been a constant challenge to try and see how we can make the data and the resulting knowledge that is generated by those data analyses, how we can make them locally relevant and, if you will, communicate them back, make sure that they are being used at the local level, which in itself is a good thing, but also fundamental for the very long-term sustainability of the whole setup, because obviously participants will only continue to be involved if they get something useful out of it, if they think that it's worth the effort of spending time and resources in in that network. And for academics, those results, the benefits are quite clear. Data which can be published, lead to publications, etc. But for the local actors, obviously what they want to get out is knowledge that they can locally use that improves the land management and increases the benefits they get from managing those regions. And so we've been lucky enough to, when thinking about that, to get some funding from research programs like ESPA, Ecosystem Services for Poverty Alleviation, and later on SHARE, that allows us to do a bit more thinking about that aspect of long-term sustainability and the way that knowledge is being created within such a network, and how to make sure that it feeds back and is of use to all the involved actors. But basically the whole network represents a win-win situation for everyone who's involved, which is obviously the only way to make it fair, but also necessary for the long-term viability and sustainability of the activity in itself. And so we teamed up in those research projects with social scientists and did a bit of an introspection, if you will, a bit more theoretical thinking of how to do that best, and what are available methods and tools that we can use to do so. And obviously, when we started that process, we directly identified that there's strong analogies with citizen science, and in a way, we kind of invented a type of citizen science. But thinking a bit more, obviously, what we did within EMEA is quite different from the more traditional citizen science. When you say citizen science, people might think rather, for instance, about, say, citizens in London going to the park, making pictures of birds and using that to identify species. The type of activity in EMEA is obviously quite different. And so to get our head around the different types of citizen science and their major characteristics, the framework published by Muki Haklai from UCL, the group of extreme citizen science, was very useful. And that's the one that is shown here. And Muki essentially identifies 4 types of citizen science, of which perhaps type 1, crowdsourcing, is perhaps the best known one, where citizens are mostly involved in the data collection. Citizens are sensors, which obviously these days with mobile phones has become much more widespread, and a lot of mobile phone applications being developed for that purpose. But there are others which involve citizens more in the context of interpretation of the data. That's what Muki calls distributed intelligence. Then participatory science, and that's probably more what EMEA does, where participants are involved in aspects of problem definition and data collection. And then the last part is what Muki calls extreme citizen science, where really citizens are involved in each of the steps of the formal knowledge generation process, fully collaborative science. And so probably where we are with EMEA is 3, perhaps with the ambition to really get to 4, in the sense that at this moment most of the analysis is done by academics, but it would be great if we can really involve other non-academic partners more in that aspect of the analysis. But I should highlight that these 4 types are definitely not is not a ranking where 4 is better than 1. They're rather really just different types of citizen science, and obviously a crowdsourcing initiative in itself can be highly valuable and perfectly fine as long as people are happy with contributing and long-term sustainability is achieved. So they're really different types rather than levels or of different types of quality. But so we thought a bit further about that and said, well, how can we actually optimize that involvement and the benefits that each actor gets out of that whole process of generating knowledge, where the final aim of an initiative like EMEA is really to try and co-create locally relevant and what social scientists call actionable knowledge that can be used by each of the the actors to fulfill whatever their goals may be, from simple intellectual interest to getting information that helps managing their water supply, their irrigation system, their land. And so doing that, we came up with this framework that basically follows the traditional workflow of knowledge generation, especially in natural sciences like hydrology, which typically has three different aspects: data collection, observations, typically with instruments, then processing, making sense out of the raw data sets, the raw time series as they come from rain gauges and river gauges, and lastly, communicating, interaction, and making sure that the knowledge is distributed and reaches everyone, but at the same time, that is also the moment of ideation where knowledge gaps are being identified, which prioritize and help identifying the next step in the circle, because indeed it's very much an iterative circle of data collection, interpretation, identification of knowledge gaps. And so this framework allowed us to then think about each of those steps and think, well, what can we do better to maximize the involvement and make these processes both more inclusive but also more effective and useful. And all that sits within a broader theoretical context of polycentric governance, to which I'll come back later in my talk. But now I'll go through each of these steps and show a bit how EMEA evolved and what ideas we had to improve those different steps. And let's start with ideation, because it's really fundamental in an initiative like EMEA to make sure that we get a common, or that we unite, gather people around a common interest and a common goal. And I think that's probably one of the major reasons of the success of a network like EMEA, that we, mostly by accident, because obviously we didn't have a plan at that moment, but that we identified that kind of common goal, which combines locally relevant questions. And here on this slide, you can see some of those rather specific questions that local communities and local actors, like local NGOs, have about managing their ecosystems. What is the impact of how do the different systems function, and what is the impact of management, but with a kind of underlying common scientific bottleneck, which in this case was the lack of data, the lack of hydrological data. I think that really is a very fertile ground to join force and say, well, let's join and put things together and see whether we can do something useful and team up and solve these questions and make that as efficient as possible. And so that's where we started. And then obviously the next step was to collect data. And also here, I think more broadly in citizen science, there's perhaps two major types of data collection that can happen. Where perhaps the most well-known one is the context of crowdsourcing, where citizens use, for instance, a mobile phone to manually collect data. And obviously there, the power of the crowd is very, very clear. The more people you've got to collect data, obviously the more data that can be collected and the further you get. So that is one way of collecting data. But in EMEA, we went a different route, in the sense that in hydrology, very often we rely more upon continuous or long-term data sets, continuous time series or regular time series for processes like river flow, precipitation. And so their manual measurements are very cumbersome and probably not the optimal way of doing things. So we rather started exploring and the use of automatic equipment, but then making that as low cost, but also as robust and as relevant and useful and applicable as possible within those contexts. Having to solve some issues, not only of the fact that commercial equipment is quite expensive, but also has issues like, for instance, the software to connect to commercial sensors is not always available in Spanish, which in our case was, for instance, a major bottleneck to train local technicians to read out the data. So that was the reason to explore new technologies and even build our own sensors. And actually, that in itself has spiraled a bit out of control, if you will, or become successful in the sense that we've applied that not only within EMEA, but also in some other projects and building low-cost sensors for water level measurement, and for instance apply them in the context of flood early warning systems in Nepal, where again the institutional network of water level measurements doesn't reach many of the places that are under severe threat of flooding. Or a very different context, using low-cost LiDAR sensors to measure the water levels in ground or in Handa groundwater wells in places like the Horn of Africa, which again is a region where traditional monitoring is not very convenient or very challenging to do, and where low-cost equipment can provide or can fill a niche and fulfill a role in increasing data collection in the context of, for instance, drought mitigation and management. And that's essentially the only reason we could do that, was building upon this vast range of available technologies, which I would call the open hardware ecosystem. And surely many of you are familiar with platforms like Arduino, Raspberry Pi, which really give, if you will, a box of Lego blocks that makes it very convenient to combine, tailor, and develop technologies to build tailored and optimized logger systems. And here's just an example of, for instance, how we managed to use Arduino technology to build a power optimized logger system, combining CPU, battery, storage, and telemetry, all in a PCB that is smaller than the size of a deck of cards, and gives us the flexibility to connect a large range of sensors, which also have mushroomed from extremely low cost sensors for water level, soil moisture, and others, to, if you want better quality, the possibility of even attaching commercially available sensors to those logger systems, and drive down the cost, but also tailor and optimize applications for very specific purposes. So here we're really standing on the shoulders of giants, if you will, and making best use of that tremendous opportunity and availability of open hardware and related software that has emerged over the last decade. Because data is only as useful as the information and knowledge that you can extract from them. So another aspect we spent some time thinking was how we analyze the data that come from that monitoring network. And in this case, we focused a lot working with our local counterparts to see how we can analyze and present the information in a way that can support local ecosystem management. And there, particularly, the interest was, as I mentioned earlier, on evaluating different types of land management, roughly categorized in cultivation, livestock grazing, and forestation, and visualize that and communicate that with easy to interpret indicators and graphics that help local managers to make decisions about the best type of management, which obviously is very context dependent, because obviously water is one ecosystem service, cultivation and even forestation are others. And so it's easy to say, or to tell a local farmer, no, you can't farm or you can't plant any trees because the downstream users need the water. But at the same time, the local farmer obviously needs to make a living. So trying to balance out and decide whether what is in a specific context most valuable, having more water or having wood to sell, is obviously something that sits in, or a decision that sits in the hands of a local decision maker, where scientists obviously try and provide as much quantitative evidence as possible to facilitate and support that decision. And that's very much the context in which we try to analyze, present, visualize the information we got from that network. And lastly, the communication is obviously also a very important aspect, not just to make sure that the scientific analysis reaches the end users, but also as a way to integrate different types of knowledge bases. And that's, I think, the key element there is to facilitate a multi-directional exchange of knowledge, to really make the best out of the different types of knowledge, from scientific knowledge to local expert knowledge, and bring that together and maximize the evidence base for decision making. And also here, there's a lot of interest in using ICT, and especially these days that we're all working from home and getting very familiar with virtual methods for knowledge exchange. Obviously, there's a great opportunity to leverage those in the context of citizen science and distributing and facilitating interaction between the different actors of a citizen science project. But that said, especially within EMEA, I think we're still very strongly convinced that meeting in person, sitting together, discuss, exchange ideas is still by far the best way of doing that. And indeed, within EMEA, we've set up what we call yearly assemblies, where the whole community tries to come together and discuss and exchange ideas, solve issues, brainstorm, and that constant interaction and communication between the different actors is really fundamental to keep that momentum and steer the whole activity and initiative in a way that maximizes the usefulness and buy-in from everyone involved. And again, I think that essentially comes down to building a community of practice, gathering people around a common goal, and try and reach that together. But that said, obviously, we can't constantly be together, so it's great to try and complement that with digital opportunities, and their mobile phones, cheap tablets, internet connections, etc., are a great opportunity to maximize that, but at the same time require us to think hard about how exactly to convey, to communicate, to visualize information for different types of end users. And particularly a former PhD student of mine, Zetzel Kavli, has done some great work on thinking how to implement a user-driven co-design process to develop some of those tools, because those tools have a bit of tendency to be strongly driven by technological possibilities rather than end user needs, and that's probably one of the main pitfalls or risks of this kind of activities. And then lastly, I mentioned polycentric governance, and I think that has been very important for us to think more about the implications of citizen science and this kind of new type of knowledge generation within the broader context of a water supply or hydrological system. And indeed, think about the relevance or the implications for the broader governance at the level of a catchment and beyond, where we think that there's probably a bit of a change in the way that hydrological knowledge is generated, which historically was very much focused on maybe not monopolies, but a few dominant actors that had the governmental mandate to collect data, institutional monitoring, like the Environment Agency in the UK. Well, obviously, the opportunity for non-institutional actors like NGOs, even local communities, to generate their own information has big implications for aspects like power relations, the type of dialogue that different actors have within a system, but even aspects of credibility of knowledge sources. And obviously, that has very profound implications for the way that water systems are being governed, with a great opportunity to provide complementarity. And I think that's very much the space that an initiative like EMEA wants to occupy, but at the same time, obviously, also risk for conflict, especially if different data sets do not agree on the story they tell. So very important to think much more broadly about the consequences for the governance of water and related ecosystem services. And there, the theoretical framework of polycentric governance, which was originally coined by Elinor Ostrom in the context of city management, and later on the management of common natural resources, has proven to be very very influential and very, very useful to think about how a system migrates from a rather monocentric system to a polycentric type of knowledge creation, and how that needs to be managed to do that in an optimal way, ensure complementarity, ensure resilience, and avoid and minimize the risk for potential conflicts that different knowledge bases might not agree with each other. And as an engineer, I step a bit outside of my comfort zone telling that, because obviously that's the realm of social scientists, but it's been very, very interesting to participate in that process of thinking of the role of citizen science within broader governance of water resources systems. And then lastly, let me finish off with just quickly highlighting how EMEA has contributed to a very specific management and governance question, which is that of nature-based solutions for water security in the context of the city of Lima in Peru, which is very much a water constrained system. Lima is sometimes coined as the second largest desert city in the world, because it's located at the coastal desert near the Pacific, annual rainfall regime of around 20 millimeters a year, but receives water from those water towers, the Andes, which sit nearby, and which receive rainfall overspilling or spilling over from the much wetter Amazon basin. So these are really the natural water towers for Lima, but at the same time, systems under severe stress with a lot of human activity, agriculture, but also aspects like, for instance, mining, which provide or pose a significant threat to the system. And at the same time, the system is really running at its limits, because Lima at the moment has already more than 10 million inhabitants and is still growing at a very fast pace. And so luckily, there's a lot of interest in trying to find ways to manage that system sustainably, and a particular interest in applying nature-based solutions to complement the existing grey infrastructure of reservoirs and canals that is already in place. And that obviously sits within a much broader international interest in nature-based solutions for water security, witnessed, for instance, by the United Nations report on the World Water Development report that came out in 2018 about nature-based solutions. And so this is the context. So Lima itself is pretty much sitting in a desert. That's what the landscape looks like around the city. And on the Peruvian coast, very small, low amount of rainfall. The mountain regions, the highlands nearby, have a much wetter regime, but still very, very seasonal, and highlighting the need to store water to overcome that dry season. And that's very much where the interest of local water management lies. And a particular intervention of interest is one that's called Amuna, which essentially is an artificial recharge system that has been operated and has been implemented for hundreds of years, where local communities in the highlands diverted water from small streams, typically high up in the mountains, 3,500, 4,000 meters altitude, divert water into what is essentially a leaky canal that allows water to infiltrate in the hill slope, similar to the concept of managed aquifer recharge, but in this case, much smaller aquifers, or rather hill slopes that have a residence time of a few weeks or even months, but still therefore allow more water to store and delay it to increase water availability during the wet season, or the dry season, or at least the start of the dry season. And so this system has existed for centuries, but wasn't really on the radar of the water managers in Lima, because it's never been really hydrologically characterized. And that's exactly what we did with an EMEA site, team up with local communities to collect hydrological information, rainfall, river flow, and do some simple tracer experiments to estimate the transit time of the water within those hill slopes. And then we used that information to do some analyses and do some simulations of what would be the impact of deploying this kind of intervention at a larger scale within the Rimac River Basin, which is one of the main sources of water for the city of Lima. And that model allowed us to compare the different hydrological regimes. Here in blue, the original natural regime, in red, the regime including the existing grey infrastructure, and then in green, the simulation of how the natural infrastructure, especially the amunas, could contribute to further reduce the wet season flow and basically buffer increase the dry season flows. And I don't have too much time to go in detail, but you can read up the publication of Boris Ochoa in Nature Sustainability to get the further details. And I think one of the key the key lessons of this simulation was that it's clear that nature-based solutions will not be able to replace the grey infrastructure, but it can complement it. And basically the combination of green and grey makes the whole system more efficient, more adaptive, more flexible, and also more efficient in terms of water resources management. And that obviously is a very important lesson that can be integrated and is these days integrated in the water management plans of Lima. And that's all I wanted to tell you. So I hope you find that interesting. Obviously, more than happy to answer any questions, and just finish with another experiment that we did to visualize and communicate our findings of the hydrological functioning of Amuna. In this case, not through ICT, but more a static infographic, which helped explaining the Amuna system for the city, or the inhabitants of the city of Lima. And part of the PhD work of another PhD student of mine, Sam Granger, who has also published his findings. Good, and it rests me only to thank you for your attention, and also thank the several funders, as well as obviously the whole network and participants, the community of the EMEA network, without whom obviously nothing of this could have been realized. So thank you very much, and most happy to take any questions.
Thank you, Wouter. That was really great. We've got several questions in the chat. In fact, someone has asked the question I was going to ask, so I will save it for then. Perhaps I'll read the question. Cameron asks, what are the most effective methods of collecting river data for further processing? Perhaps in the Andean context, I'm guessing.
Yeah, that's a really good question, and obviously it strongly depends on the context. But in our specific case, we focused on monitoring small upland catchments, mostly because they have relatively homogeneous land use, and they are most effective to identify the signal of land use change, or differentiate between different types of land use. And so for that, as you could have perhaps seen from the photos, we used V-notch weirs in combination with water level sensors, and that is as long as you're able to implement or to construct the V-notch, the most convenient way to collect highly accurate water stream flow data, in the sense that you measure water level, and then you use the V-notch weir equation to convert it to river discharge. But obviously that is only possible in small catchments. Unfortunately, there isn't yet an ideal solution to measure the volumetric river flow directly. So in our case, even in larger catchments, we've often used water level measurements as a proxy, which we then convert into discharge with a rating curve. But there are other more novel technologies. Particle image velocimetry, for instance, is a way to get surface water velocity. So within the hacker and new technology space, there's a lot of new technology that can be explored.
Great, thank you. The next question is about the risk to the participants. So Kizar asks, how should the risk, for example, the risk of falling into the river, the risk to individuals be mitigated if citizens are encouraged to participate?
Yeah, so that's a very important aspect of citizen science, or indeed any participatory activities. I guess the best thing to do is make sure that you've got an appropriate risk assessment in place, and obviously that depends on on local regulations, but in essence, obviously, you want to keep everyone as safe as possible. So yeah, make sure that you assess all the risks and have appropriate mitigation strategies in place. But obviously, yeah, it's definitely an important thing to keep in mind, that if you invite people to participate in any activity, that there might be risks involved, and that you need to be very transparent with everyone about those risks and about what to do if something goes wrong. But yeah, try and be as safe as possible, obviously.
Yeah, safety first, always important. Nick Everard, you've asked the question I was going to ask, so I don't know if you want to ask the question. Do you want to unmute yourself?
Okay, yeah, thanks, Lucy. Yeah, well, I'll try and ask it as well as you might have, but yeah, you touched on it, but do you have any examples where citizen science information has been combined with that from statutory monitoring authorities? And, you know, if so, any insights into what are the issues and how effectively things like data management, ensuring quality of the data, and sort of resharing that data, you know, if it's made available so people know where it originated. But yeah, examples of combined citizen science and statutory information.
Thanks, Nick. Great question, and good to see you here. Yeah, I think that the best example is Peru, because they are actually the local environment agency is involved as a partner in the IMEA network, and it's actually interesting to see how their stance has evolved from, in the beginning, perhaps being rather skeptical, up to even a bit of a protective stance of saying, oh, but we are the experts, what are you going to do, to a much more positive approach to really see the value of combining and filling the gaps, if you will, which are inevitable given the constraints on resources of institutional monitoring. I don't think we're to a level yet where they really integrate the citizen science data within their own monitoring or their own data sets. But what does happen is that we create derived products that integrate the two data sources, taking into account, for instance, aspects of different accuracy, different uncertainties, different methods. So you need to do a good job with trying homogenizing them, or at least making explicit the different characteristics of the data sets. But once you integrate them, you can do very, very useful analysis. And I think there's been some good examples of how combining the data sets has been useful for analysis, like, for instance, the impact of elevation or the elevational gradient of precipitation in along the slopes of the Andes. So I think that the key element is not really trying to fully integrate them, but in a single data set, but just combine them in derived data sets that allow them, or that allow analysis of the of integrating them both in scientific analysis. I think that's very much the stage where we're at least within EMEA.
Thank you.
Great. The next question was from L. von Benzen. If you would like to unmute and ask your question.
Hi, yeah, thank you. So I was just wondering if you could explain a bit more about the design of the low-cost wireless sensors that you developed for use by citizen scientists. I know you mentioned that they were measuring water level primarily, but yeah, just a bit more information on that would be great.
Yes, so this is really where we leveraged a lot of existing open source technology, especially the Arduino system, which is essentially a small computer, but with what is called a real-time operation system. So it's the big advantage is that it's very power efficient and also relatively low cost. You can have an Arduino board for less than £10. And so we basically taken those designs, which are indeed the open source domain, and tweaked them for our particular application. And a few things that we've tweaked is power efficiency, because we're working in very remote areas where even installation of solar panels is not always feasible. So we wanted to make a system that can last for many years on a single battery, and that's again the big advantage of systems like Arduino, that you can make them very, very power efficient, very small. And then in terms of telemetry, I think that is still a big challenge. The default telemetry is via the mobile phone network, and in some places you can even make use of more newer 4G IoT types of protocols. But obviously, in many cases, especially remote regions, you don't have mobile phone coverage. And their potential intermediate solution is to work with, so to set up local networks. LoRa, for instance, has become very popular to at least store data in a central node, so you don't have to visit every single sensor, or perhaps route the information, the data, to a location where you can connect to the a mobile phone network, or in the worst case, use satellite transmission, although that's obviously both very power intensive and very expensive. So also there, I think the bottom line is that there's a lot of new technology that can be explored and leveraged. And I'm happy to give you offline more details about our specific solution, but it's just one along very many that exists in the broader community.
Great, thanks. It's amazing how cheap these bits of kit can be, computing with the Raspberry Pis and Arduino. Next question we have is from Charlie Bleasdale. If you would like to unmute and ask your question.
Hi, can you hear me?
Yes.
Yeah, my question was more about sort of data quality and how you manage that, because with all this sort of using mobile phones, you sometimes can have issues with the sort of quality of the data. So I was just wondering how you can sort of check the data and then sort of ensure further down the line that you've collected the high quality data and there's no sort of errors.
Yeah, I think that's a very relevant question, and indeed one that comes up very, very often. And fair enough, it's easy to talk about low-cost technologies, but the fact that high-cost technologies still exist doesn't mean that they have an advantage. And often, indeed, low-cost technologies have trade-offs in terms of lower reliability or lower quality. And I think that the key element there is to think about what is the most appropriate sweet spot, if you will, between quality and usefulness. And I think overall we're quite happy with the quality of the data that come from EMEA, but obviously inevitably it's very important to do a rigorous quality control. I think that's fundamental, so that at least you know what is the potential range of error and uncertainty. And I think another important aspect is that we should avoid trying to think about institutional data good, citizen science data bad. All data inevitably have an uncertainty attached to them, and indeed the high quality instruments will probably have a lower uncertainty. Lower quality instruments will have a higher, but as long as we quantify them and we're aware of those uncertainties, and it shouldn't be a problem to combine them in analysis, statistical methods to deal with uncertainty, but also to think, well, what is good enough a level of quality for a certain type of analysis. And I can directly think about certain types of analyses, long time series analysis, for instance, for which the EMEA data definitely would not be suitable because of their nature. But other types of analysis, they really turn out to be quite powerful. So I think again, it's a matter of quantifying uncertainties, be very clear about where trade-offs are being made, and at the same time use that to think about what is the optimal quality that is needed for a particular type of purpose. And obviously, a citizen science activity will often have a very different purpose than a long-term institutional monitoring activity. So all about trying and quantify those uncertainties.
Brilliant, thank you.
I think that's pretty much taken us to 2 o'clock. Thank you all for your questions, and particularly thank you to Wouter for the amazing presentation, really interesting. Thank you for joining us, and remember to keep an eye out for our future webinars. There's one at the end of next month and one at the end of April, and we'll be scheduling some more. throughout the year as well. So hopefully we'll see you again soon. Thanks. Bye bye, everyone.